Okay, so we're just gonna have a quick video on how to encode a linear transformation with a matrix. So if there's two ways to do this. One way is just to kind of strip off the coefficients. So for example, if we take a transformation, and this one we're gonna go from R3, because we have 3 inputs, to R2. So it might have a formula that looks like that. What we're going to do is we want to strip away the coefficients in just the right way that will give us the matrix. So keep in mind that if we have a matrix and we multiply x, y, z, this is going to give us a 2 by 2. So we're going from R3, here's R3, and this is R2. So the end result, if we multiply this matrix across, we're going to end up with something times x plus something times y plus something times z for the first entry. And likewise, we're going to end up with the same thing on the bottom. Now, it's important to understand that these right here could all be different. These don't have to be the same. Right? So these can all be different numbers, but we want to fill them in. And so a good way of coming up with the transformation is to put the formula in precisely the form that I've written. So I want to write this very precisely as something times x plus something times y plus something times z. And now what we're going to do is we're going to just translate this. So there's a 1 here, so that's a 1x. There's a 1y, so that's a 1. But there's no z's. There's right here, there are no z's. So this is going to be a 0. Right? Now I've written this in kind of a tricky way. Here I put z's first. So the coefficient on the bottom is 2. And there's a 1 for x. And likewise, we're missing a y. All right. So now the beautiful thing is these coefficients are encoding the matrix. This tells us very specifically what that matrix is. We can literally just take the coefficients like this. And now if we were to go ahead and actually multiply out what the matrix multiplication does. So let's just do this real quickly. What's going to happen? Well, on the top, we're going to do the first entry 1 times x. So we just get x. We're going to get 1 times y. So we're going to get a plus y. Let's put that in orange just for emphasis. Right. And then lastly, we're going to get 0 times z. Or there's nothing there. Right. And we can do the same thing on the bottom. We're going to get 1 times x, 1 times our x. So it's going to give us x plus 0 times y. So 0 times our y. And finally, we have 2 times our z. And so if we multiply out the matrix, we'll notice that that's exactly what the original transformation is. These are the same thing right here. So one way of encoding a transformation is just strip off the coefficients in exactly the right way. Keeping in mind that if something's missing, you're going to replace it with a 0 in the matrix. And you have to make sure that the coefficients are in the same manner as the inputs. So for example, everything, because I've formulated z as a third input, all the coefficients of z have to be in the third column. X is the first input, so all of the coefficients of x are in the first column, and so on. So this is kind of an easy way to encode a transformation. One thing I don't like about this, even though it's easy, is that it doesn't really tell you what a matrix really is. So this is really good for computing things and getting started and crunching the numbers. But one thing I want you to keep in mind is that a matrix or linear transformation also encodes geometric information. So let's do another example. So we're going to define t, but now I'm not going to define it with algebras or a formula. I'm going to define this as rotating xy by 45 degrees counterclockwise, then stretching by a factor of 2. right? So this is a lot of words, but this is something that you might want to model, right? Something physically that's happening that you want to have a formula for. So the question is, what's the transformation? What's the matrix that encodes this particular transformation? One thing to keep in mind is that if we're going to encode a transformation as a matrix times or a vector, or maybe more simply, we can write it like this. This matrix M, this first vector here, is just going to be what happens to the first standard vector, the 1, 0 vector. So we call this a standard vector. And the second vector, the second one would be what happens to the second standard vector. And if you had more inputs, you go to the third standard vector, and so on. So all we need to do to compute this transformation, it sounds like a laborious, impossible task to figure out exactly what the transformation is, but all we have to do is figure out what happens to the 1, 0 vector, and also what happens to the 0, 1 vector. So there's two different vectors. We have to just figure out what happens to them, and that's going to give us our matrix. All right, so let's go ahead and just perform this transformation on each of these vectors. So the first vector is the 0, 1, the 1, 0 vector. There we go. And the definition of this is that we're going to rotate it. It's going to rotate 45 degrees. And then we're going to stretch it by a factor of 2. So in trigonometry, when we rotate it 45 degrees, it's going to go to square root of 2 over 2, square root of 2 over 2 right here. That's what that point is. And when you multiply this by a factor of 2, when it's full, that's going to be square root of 2, square root of 2. So that means this whole vector right here, the final vector that you're going to get is going to be square root of 2, square root of 2. That's just using trigonometry. So we went from 1, 0 to square root of 2, square root of 2. All right. So now we can do the same thing for the other vector. Now the only difference now is what's the other vector? The other vector here is 0, 1. So what's going to happen? It's going to rotate 45 degrees. And that point is going to be similarly minus square root of 2 over 2 square root of 2. And then when we stretch that by a factor of 2, what's going to happen is it's going to go all the way out to square root of 2 square root of 2. But the first one's a minus. My apologies. So that tells us that we're going to go from 0, 1 to minus square root of 2 over 2 for the second vector, and 1, 0 to square root of 2 square root of 2 for that. So what we're going to do is we're literally going to concatenate these two vectors. We're going to concatenate these vectors. And this is going to give us our matrix. So keep in mind, the first one was what happens to the first standard vector, and the second one is what gives us the second standard vector. And so what's our final matrix? Our matrix M, or A, whatever you want to call it, is going to look like this. You're just going to concatenate them together. And this seems magical, right? But part of the linearity says that once you know what happens to enough of the vectors for a linear transformation, it has to define it all, because you're not allowed to have too much craziness going on. It has to be a very simple function. So simple that just like a line is defined by 2 points, a linear transformation is going to be defined by a very small number of points. In fact, if your input dimension is 2, it's going to be defined by two points. 3 inputs, 3 points, and so on. So that's our matrix. Now this might seem magical, but let's just do a sanity check. Let's make sure that this matrix actually does what we want it to do. So let's just do a final check. Let's take this matrix and we're going to multiply it by the point minus square root of 2 over 2 square root of 2 over 2. So why am I picking that point? We're just doing a check. We're just going to practice everything that we've done so far today. This particular vector right here lives on the unit circle at 45 degrees. And we know that according to the definition that we gave geometrically for this transformation, that we're going to rotate 45 degrees, and then we're going to double it. So if this matrix works, we're going to end up with 0, 2. So let's see if that actually happens. So let's do some matrix multiplication. What do we get? So the first one, keep in mind we're going to take the first entry times that one. So that's square root of 2 times square root of 2 over 2. So that ends up being a 1. All right, so just square root of 2 times square root of 2 over 2. These guys become 2, and then we divide, and we're going to get a 1. So that's what's happening there. And then similarly, when we multiply minus square root of 2 times that one, we're going to get minus 1. And so we add those together. So on top and D, we get 0. And then on the bottom, we're going to do the same thing again. We're going to multiply square root of 2 times square root of 2 over 2. And that's going to give us a 1. And finally, when we take the same thing, we're going to do the same arithmetic. We're going to get plus 1. And all together, we indeed get 0, 2, just like we predicted. So this matrix seems to do exactly what we indicate. We defined the transformation geometrically, saying this is just a stretch, it's just a rotation. And then we found the matrix. It seems weird that there's some matrix that, captures this very specific geometric transformation very specifically, but it does. And there it is. So that's another way of finding a matrix. You don't actually need a formula as long as you know what happens to a very small number of vectors, and in particular, if you can figure out what happens to the standard vector.